Hello everyone, I would like to quickly introduce myself and my team members. I am Simran Jadhav and my team members are Kaustubh Khavnekar, Aniruddha Mesri and Anuj Singh. We all are from instrumentation department and our project guide is Ms. Kanchan Chavan. So today we'll be giving a presentation on our BE project, that is development of LIDAR like systems to measure object distance. The contents of our presentation will be as follows. Introduction. So we are going to develop a handheld device based on LIDAR principle that will measure distance through light waves. As you can see in the image, we are going to develop this type of device. What is LIDAR? LIDAR stands for light detection and ranging. Each time the laser is pulsed, laser generates an optical pulse. Then this pulse is reflected back and it is received by the receiver. And then high speed counter measures the time of flight from start pulse to the stop pulse. Block diagram. As shown in the diagram, laser source transmits the laser. So when the user presses the start button on the device, laser diode emits laser. Start pulse is generated at this time event which is connected to TDC. This laser reaches the destination surface and gets reflected back. Photodiode receives the reflected light from the target. Photodiode output is converted into voltage and also amplified by a transimpedance amplifier. This amplifier output is provided as a stop signal to TDC. TDC provides digital output corresponding to time difference between stop and start signal. TDC stands for time to digital converter. This digital code is received using a microcontroller. Also, all the timing signals needed for the operation of this device are managed using a microcontroller. Software programs can be developed in microcontrollers to convert digital code into distance or speed. Further slides will be explained.
So the first method is using ramp and ADC. That is in this the ramp and ADC method, as we will give the start pulse, the op-amp based integrator circuit will generate ramp signal. As laser will get on, start pulse will come and it will start generating the ramp, and if on 5 volt we will get the output and it will reach in 25 microsecond to 5 volt. Then this ramp, as it is analog voltage, we have connected it to the input of ADC and we have used 16-bit SAR ADC, that is successive approximation ratio. Then ADC will digitize this voltage. Therefore, for long distance measurement we will get the ramp voltage more, and for short distance ramp voltage will be less. The number of possible values that can be represented by integer bit calculated using 2 raised to n, where n is the bit depth. Therefore, the 2 raised to 16, as we are using 16-bit ADC, we will have the possible values of 65536 numbers, and the for 25 microsecond we are getting the 381.4 picosecond as the resolution, and if we will take it as 100 nanosecond, we will get the resolution of 1.52 nanoseconds.
So this is the second method, which is digital counter method, where 3-bit binary ripple counter is used. Initially counter count is 0. We give clock to first flip flop and then the output of it changes from 0 to 1. So when laser is on, start pulse is given, counter starts counting, and when the beam of laser is reflected, photodiode detects it and stop pulse is received, and we get time of travel. When stop pulse is received, stop the clock of the counter and count gets latch. So for example, if my count is 1, then how much is my time interval? For example, 20 megahertz clock, it gives one clock period of 50 nanoseconds, which is derived by this formula: f is equal to 1 by t. F is frequency, therefore 20 megahertz is equal to 1 by t. T is time interval, that gives me t is equal to 1 by 20 into 10 raised to minus 6 seconds, which gives the time interval of 50 nanosecond. So if only one clock count is there in time interval, then my resolution is 50 nanoseconds. If two clock count is there in interval, then my time interval is 100 nanosecond. So with this method we can know the lowest possible time interval which can be measured is equal to the clock period of the clock given to the counter. If 100 megas is used, more speed is achieved. 1 gigahertz is used, 1 nano time interval clock, 1 nano time interval is measured. So next is a transimpedance amplifier, which is LF356, which is basically a current to voltage converter, and its pin configuration is this. So in this video we have given 12 volt input supply. When the laser light falls on photodiode, the photodiode detects the light and produces a current signal. Then this current signal is given to the transimpedance amplifier, where it converts the current signal into voltage signal, and this voltage signal can be seen on the digital multimeter. And on DSO we can observe that waveforms are generated and the voltage value changes from 0. The photodiode which we have used in this hardware is PDB-C156, which is very sensitive and operates in the range of 400 nanometer to 600 nanometer range.
Is the comparison of PIC, NXP, and Nucleo series STM. In this, the as you can see, the internal ADC of PIC controller is 16-bit. NXP is also NXP controller is 16-bit, and for STM it is 12-bit. ADC type for PIC is Sigma Delta ADC, and in NXP SAR ADC is used, and in STM MSPS ADC is used. So as we can see, the clock frequency of NXP is also 48 to 60 megahertz, which is good enough for us, and the power consumption is low, and the most importantly the ADC, we are getting this RADC of NXP in NXP as 16 bits RADC. So we are going for that. Talking about the NXP kinetics, this board, this Freedom KL25Z is ultra low cost development board by Kinetis, which utilizes the ARM Cortex processor. This is very energy efficient microcontroller. It has 128 kilobytes of flash and 16 kilobyte of RAM. This is also fully featured demo board, which is available in the. So these are the milestone of our project. The first and second milestone we have already achieved that. The third milestone that we have right now is the procurement of NXP board, laser source, and photodiode that we will be doing in this month. And the fourth fifth milestone, we will do it in the future. We will achieve that in future. So thank you for patience listening.